All right, guys, in this lesson, we're going to look at the topic of momentum. This is, if you are studying IB, this is topic 2.4, momentum and impulse. This video will be talking about momentum and the conservation of momentum. So, what does it mean? Conservation of linear momentum. First of all, linear is a good hint that we are going to be dealing with objects that are actually traveling in a straight line. That makes our calculations very nice, very easy, because we assume that things can only go left or right. So the example I use of a more complicated situation would be dealing with collisions on a pool table or a billiards table in which balls can ricochet and collide and travel in all sorts of directions on that two-dimensional plane. Picture a bird's eye view looking down over a billiards table. You'd have your billiards table and you could have balls running into each other and colliding and ricocheting, and this would be a two-dimensional scenario because you'd almost have like a y and an x graph. We are not going to deal with anything that complicated because that would require trigonometry. We would have, SOHCAHTOA, that classic sine, cosine, tan formula, and you could calculate this. You could still use the conservation of momentum. However, it gets a little messier using the trigonometry, which we do use in this course. So that is actually a great extension or challenge for this. Once you're confident with this, try and see if you can come up with a conservation of momentum calculation when you have collisions that are sort of more so angled, much how two balls collide and then they keep rolling in two separate directions. That is two-dimensional. We're going to look at sort of a one-dimensional scenario right now. So, what is momentum? It's kind of like thinking what makes an object hard to stop. You can think about things like bullets and trucks traveling on highways. Which one is harder to stop? It's a great question. Obviously, we need a little bit more information to truly have an answer, but you might have some guesses or estimates as to which one you think is more difficult to stop. Momentum. If we think about a bullet, let's just think about two bullets right now. If you have one bullet that's traveling twice as fast, or we could say with twice the velocity, it would make sense to believe that it would be twice as hard to stop. I think that's fairly logical. If we now think about two different trucks with different masses, it makes sense to believe that a truck that is twice the mass would also be twice as hard to stop. So think about that. I think how hard it is to stop something or how difficult it is to stop something must be linked to its mass and its velocity. Let's take a look at our equation for calculating momentum, and there we have it. The momentum of an object is directly proportional to its mass times its velocity. So we have mass, we like to use the SI unit kilograms, velocity in meters per second. So when I multiply an object's mass times its velocity, I should get its momentum. What are my units for momentum? Well, for momentum, as long as I keep my units in kilograms and meters per second, then my answer should be in kilograms times meters per second. Notice this notation. It's important that you're comfortable with this. This is no different than, and here as well, this is no different than meters per second, but it is preferred. It's important to be able to switch back and forth between the two as well. So momentum is mass times velocity, where mass is given in kilograms. Make sure you're comfortable converting, especially between grams and kilograms. But it's good to practice a few. And then velocity, meters per second. An easy example, okay? If you're given a question or a problem where you know the mass, which we do in this case, we know the mass, and we know the velocity. What is the momentum of this truck. Easy. We know that momentum, P, equals m times v. I have mass, I have velocity. I go and calculate using my given formula, momentum equals mass times velocity, and I'm done. The only thing to remember is double check, am I in kilograms? Am I in meters per second? Yes, I am. So my final answer is 40,000 kilogram meters per second. Pause the video there if you'd like to take the time to work that one out. Now, that's how we calculate simple momentum situations, P equals mv. But now, what is the conservation of momentum? Or what is the law of conservation of momentum? This is it here. It states that in an isolated system, momentum remains constant. We could say that it is conserved because it remains constant. Those are kind of synonyms. Now, what does it mean to be in an isolated system? I'm going to come back to that in 1 second. But for now, let's think about that. The law of conservation of momentum states that momentum does not change, or it remains constant. That literally means when two things collide, the momentum is still conserved. The total stays the same, meaning the total momentum before the collision has to be equal to the total momentum after. And we say total, meaning there are two objects interacting. For example, one car collides with another car. That is what we're talking about. The momentum of car 1 and car 2 combined before the collision should be the same as the momentum of car 1 and 2 combined after the collision. Let's look at a real example of that. But first, I need to address this. What is an isolated system? Well, we say that momentum is conserved only if it's an isolated system because there are no other forces acting on it. What are some other forces that might be acting on things, in the real world if they're colliding? You'd have things like the force of friction and air resistance, etc. For now, we're going to almost assume that we're in a perfect world. We're in an isolated system, which means there are no outside forces taking away or pulling away any of the momentum. So let's just think about that. It's an isolated system. Let's look at an example. Okay, I call it a harder example. Of course, it's not as simple as P equals m times v. So we have a car of mass 1,000 kg traveling 5 meters per second, and it hits a stationary truck of mass 200 kg, 2,000 kg. After the collision, they stick together. What is their joint velocity after the collision? So let's keep some of these key numbers in mind. 1,000 kg traveling 5 meters per second hits a stationary truck, which means 0 meters per second, right? 0 meters per second with a mass of 2,000 kg. So it's very simple. Remember the law. Momentum before the collision equals momentum after the collision. The momentum before is easy. We just calculate the momentum of the first car and the second vehicle. So momentum of the car plus momentum of the truck before the collision. We also do the same thing after, but something's going to be slightly different because they stick together. So here's a sketch, right? We've got this truck which is not moving, 0 meters per second, but we have a mass of 2,000, so it has no momentum. Let's calculate the momentum before. The car is here. We have 1,000 kg traveling 5 meters per second. What about the truck? Well, it's 2,000 kg, sure, but it has 0 velocity. So we actually say that it has 0 momentum. So 5,000 plus 0. The total momentum before collision is 5,000 kilograms meters per second. Let's think about it after the collision. The momentum after the collision we say that they stuck together, meaning we have to combine their masses, because now we think about this as one big mass. Why? Well, they're stuck together. If these things are moving in one sort of as one object stuck together, this is one combined mass, and their velocities have to be the same because they're moving as if they are one big object or one bigger object, which now has a mass of, right, 1,000 plus 2,000 kg for a total mass of 3,000 kg. Now, what is the velocity of this larger mass? The momentum after, let's say it's 6. Well, the momentum of this big mass would be 3,000 times 6, but we don't know it, so we're going to leave it as an unknown or a variable. We don't know what the momentum, or sorry, what the velocity is after the collision, but we do know this very important detail. We do know that the momentum after should be 5,000 because it was 5,000 before. We also know that the momentum after should be whatever the mass is times this new unknown velocity. Let's tie that all together and set what we know equal to each other. If the momentum before is 5,000, right? We knew the momentum before the collision was 5,000. We saw that earlier. But the momentum after has to be the combined mass times some unknown velocity. From here, we have enough information to solve and isolate for V. This should have a little kg on it, 3,000 kg. But anyways, we solve for velocity. Kilograms would cancel off. You can do that out by pencil and confirm it, but your units will always work out beautifully. They'll cancel off. You're only left with meters per second, and you're left with a numbered value, an actual quantity. So the velocity after collision would be 1.67 meters per second. How can I double check my answer to make sure I'm right? Well, we said that the momentum before and after should be unchanged. So the momentum after should be, we said on our last slide, before the momentum before the collision, the momentum was 5,000 kg meters per second. Let's check it out after. The mass after collision, we have one big mass of 3,000 traveling 1.67 meters per second. Go ahead and punch that into your calculator. You will get the same answer. So we have kind of confirmed that momentum is conserved. The momentum before the collision equals the momentum after the collision. Something that is important to note is that momentum is a vector. We know of other vectors such as velocity, acceleration, force. What does that mean? All it means is that not only does it have a size or a magnitude, but it has to have direction. So although sometimes we just say something has a velocity of 50 kilometers per hour, that is sort of, we should have a direction on that, which in a lot of cases we're just talking about one direction, so we don't specify. But in reality, we should have a direction. Now we're talking about linear collisions. We said that we're only really focused with one dimension. So in one dimension, we have to think about objects only traveling one way or the other. Remember I said the bird's eye view of a billiards table is kind of, even more complicated than you need at this point. So we're just talking about linear travel, which is kind of like an x-axis with no y-axis. It cannot travel up or down. The simple way to think about these linear collisions is if this is what I'm calling, positive, I'm going to call the other direction negative. That is the easiest way to think about it, because now, without saying north or west or east or left and right, those are kind of, they're not vague, but it's easier to quantify something just as a positive or negative number. And that really does give us an easy description. So if this was, 5 kilogram meters per second, then this vector might be negative 3 kilogram meters per second, simply because it is in the exact opposite direction. Let's take a look at a more difficult example here. So Snoopy, with a mass of 10 kilograms, is running at 4.5 meters per second. He jumps onto a skateboard of mass 4 kg that is traveling in the opposite direction at 7 meters per second. So there's something very important about that, the opposite direction. What is the velocity of Snoopy and the skateboard after Snoopy has jumped on it? So this is a real, you can imagine this. Your friend launches a skateboard at you head on, but you're running in the opposite direction of the skateboard and you jump onto that skateboard. You're moving one way, the skateboard's moving the other way. When you jump on the skateboard, you have more mass, so you'll probably end up landing on the skateboard and sliding forward the direction you were already running. This is kind of a good graphic of how it might look. So which one do you notice is negative? Here we have a negative 4.5. Does it actually matter which one you make negative? It does not, as long as you keep track of which direction we're calling negative. So in this case, I'm actually calling this direction negative and this direction positive. Does it matter? It does not. At the end, if I did it the opposite way, I would just end up with positive 17, and I would basically just be referring to positive as the other direction. So in this case, negative 17 is referring to negative this way. You can try it both ways to confirm. You will notice that you will get the same result, except that negative 5 might mean to the left, and then if you retry it the other way, positive 5 could mean the left. You're basically choosing which way you're making negative, which way you're making positive. So let's look at this. The momentum before, let's say Snoopy here, 10 kg times his velocity. And remember, 7 and 4.5 cannot have the same sign, positive and negative. If they had the same sign, it would imply that Snoopy and the skateboard were traveling in the same direction, which is false. Okay, so we have Snoopy with negative velocity, the skateboard with a positive velocity, but it's only 4 kg. So we have 10 kg Snoopy times his velocity, 4 kg skateboard times its velocity. They jump onto each other or collide. It's like they're a collision, right? They stick together on impact. And we calculate that. The momentum of this situation in total, the total system, is negative 17 kilogram meters per second. Which direction is negative 17? In this case, I have called this direction negative. So it just means 17 to the right, 17 kilogram meters per second. That is the momentum to the right. The momentum after is, they have a combined mass, right? So the momentum after has to be this sort of combined mass. We'll call it MC, the mass of the combination of the two, Snoopy and the skateboard. So we can use this, no problem. We know that the momentum after has to stay the same. So you can sub this in very easily. The momentum after has to be the same. So I'm allowed to make this substitution. And then Snoopy and the skateboard's mass is 14 combined times some unknown velocity. So all we're doing is solving for the velocity value. Here we get this. We get this momentum before, which is 17 to the right. Momentum after is, we're not really sure, but we know it has to equal this, but it's 14 times something. My answer here, negative 1.21 meters per second. And as we say here, the negative sign tells us that the velocity is from left to right. That's the direction I chose. You could do this all the other way and you'll still end up with that direction that Snoopy was initially traveling. This is a summary for linear collisions. in the Snoopy example, we saw that they stuck together, whereas sometimes things collide and don't stick together. So there's basically, these are the two scenarios that you will have, is that you have object 1 and 2 colliding and not sticking together. So after, they will have this momentum, total momentum being the momentum of object 1 and 2. Here I use u to signify the velocity before, and v to signify the velocity after. That is a common thing we do in physics. U meaning initial velocity, v meaning final velocity. So this is when they don't stick, not sticking. Basically two things that collide and continue to be individually traveling, kind of like they bounce and continue. Whether it's in the same direction or opposite directions, we just know that they collided and did not stick together. Down below here, this was the situation we saw with Snoopy, for example. Snoopy and the skateboard each had their own independent masses and their independent velocities, independent of each other. But when they collided, they stuck together. When two things stick together, they obviously, if they're joined, they have only one combined velocity. So we only need to put a single v for their velocity. And we also see that the masses are combined. Regardless of which one you use, you can actually use this one at all times. The only difference is that when they stick together, you do end up with the ability to factor this out. So technically, this one here is additional. This isn't like something that you would actually need to memorize. You don't need this one, but it's convenient sometimes to remember that when they stick together, you're just adding the masses and you have some unknown velocity, if that's what the question is asking. Thanks, guys. I hope this helped. Please leave some feedback, give it a like, and add any suggestions. See ya.